This lesson is on solving problems involving the determination of the pH of acidic and basic solutions. This is part 3 on tetraprotic acids. Practice problem 3 is to determine the equilibrium concentration for all species in a 0.25 molar H4P2O7 solution. Determine the pH of this solution. The first ionization process is aqueous H4P2O7 or pyrophosphoric acid in liquid water partially ionizes to produce hydronium and H3P2O7- or trihydrogen diphosphate ion. Ka1, or the first acid dissociating constant, is 3.0 times 10 to the minus 2. Next, one needs to construct a Rice table. The initial concentration of pyrophosphoric acid is 0.25 molar and 0 molar for both hydronium and trihydrogen diphosphate ion. The change is minus X for pyrophosphoric acid and plus X for both hydronium and trihydrogen diphosphate ion. The equilibrium concentration of pyrophosphoric acid is 0.25 minus X and plus X for both hydronium and trihydrogen diphosphate ion. The equilibrium expression is written out where K1 equals the concentration of trihydrogen diphosphate ion times hydronium ion divided by the concentration of H4P2O7 or pyrophosphoric acid. If one plugs in the numbers, 3.0 times 10 to the minus 2 equals X squared divided by 0.25 minus X in parentheses. To determine if X is small enough to ignore, one needs to take the ratio between the initial concentration of pyrophosphoric acid and divide by the K1's value to see if the resulting value is greater than or equal to 400. In this case, the ratio equals 8, and since it is not greater than or equal to 400, the assumption that X is small is invalid. One needs to either use the quadratic equation or successive approximation method to solve for X. For this part of the problem, we will use the successive approximation method. In the first assumption, X0 equals 0, so after solving for X1, it equals plus or minus 8.7 times 10 to the minus 2. For the rest of these calculations, the positive will be used. This process will continue until two consecutive values are equal to each other. In the second assumption, with X1 equaling 8.7 times 10 minus 2, in solving for X2, it equals 2 plus or minus 7.0 times 10 to the minus 2. In the third assumption, with X2 equaling 7.0 times 10 minus 2, in solving for X3, it equals 2 plus or minus 7.3 times 10 to the minus 2. In the fourth assumption, with X3 equaling 7.3 times 10 to the minus 2, in solving for X4, it equals 2 plus or minus 7.3 times 10 to the minus 2. As you can see, X3 and X4's values are identical, so the final X is 7.3 times 10 to the minus 2. The second ionization process is where trihydrogen diphosphate ion in liquid water partially ionizes to form hydronium and H2P2O7 or dihydrogen diphosphate ion. Ka2, or the second ionization constant, equals 4.4 times 10 to the minus 3. Like before, a construction of a Rice table is made where the initial concentration of trihydrogen diphosphate ion is 7.3 times 10 minus 2. Hydronium ion is also 7.3 times 10 minus 2 molar, and 0 molar for dihydrogen diphosphate ion. The change is minus Y for trihydrogen diphosphate ion and plus Y for both hydronium and dihydrogen diphosphate ion. The equivalent concentrations are as follows. For trihydrogen diphosphate ion is 7.3 times 10 minus 2 minus Y. For hydronium ion is 7.3 times 10 minus 2 plus Y. And for dihydrogen diphosphate ion is plus Y. Now, like before, one writes the Ka equilibrium expression, but now for the second ionization process, where Ka2 equals the concentration of dihydrogen diphosphate ion times hydronium ion, divided by the concentration of trihydrogen diphosphate ion. After plugging in the numbers, 4.4 times 10 to the minus 3 equals Y times 7.3 times 10 to the minus 2 plus Y in parentheses, divided by 7.3 times 10 to the minus 2 minus Y in parentheses. To determine if Y is small enough to ignore, one takes the concentration of trihydrogen diphosphate ion and divide by its K2 value to see if its ratio is greater than or equal to 400. It turns out that the ratio equals 17, and since the ratio is not greater than or equal to 400, the assumption Y is small enough to ignore is invalid. One needs to either use the quadratic equation or successive approximation method to solve for X. For this part of the problem, like before, we will use the successive approximation method. In the first assumption, y0 equals 0, so after solving for y1, it equals 2, 4.4 times 10 to the minus 3. This process will continue until two consecutive values are equal to each other. In the second assumption, with y1 equaling 4.4 times 10 to the minus 3, in solving for y2, it equals 2, 3.9 times 10 to the minus 3. In the third assumption, with y2 equaling 3.9 times 10 to the minus 3, in solving for y3, it equals 2, 4.0 times 10 to the minus 3. In the fourth assumption, with y3 equaling 4.0 times 10 minus 3, in solving for y4, it equals to 3.9 times 10 minus 3. In the fifth assumption, with y4 equaling 3.9 times 10 to the minus 3, in solving for y5, it equals 4.0 times 10 to the minus 3. As you can see, y4 and y5's values are identical to what was seen in y2 and y3's value. So it is concluded that the result is acceptable, that the final answer for y is 4.0 times 10 to the minus 3. The third ionization process is where dihydrogen diphosphate ion in liquid water partially ionizes to produce hydronium and hydrogen diphosphate ion, or HP2O7 3-. Ka3, or the third acid dissociating constant, is 2.5 times 10 to the minus 7. In constructing the Rice table, the initial concentration of dihydrogen diphosphate ion is 4.0 times 10 to the minus 3 molar. Hydronium ion is 7.3 times 10 minus 2 molar, and 0 molar for HP2O7 3-, or hydrogen diphosphate ion. The change is minus Z for dihydrogen diphosphate ion and plus Z for both hydronium and hydrogen diphosphate ion. The equilibrium concentration for dihydrogen diphosphate ion is 4.0 times 10 to the minus 3 minus Z, 7.3 times 10 minus 2 plus Z for hydronium ion, and Z for hydrogen diphosphate ion. The equilibrium expression for K3 equals the concentrations of hydrogen diphosphate ion times hydronium ion divided by the concentration of dihydrogen diphosphate ion If one plugs in the numbers, 2.5 times 10 to the minus 7 equals z times 7.3 times 10 to the minus 2 plus z in parentheses divided by 4.0 times 10 to the minus 3 minus z in parentheses. To determine if z is small enough to ignore, one needs to take the concentration of dihydrogen diphosphate ion and divide by Ka3's value to see if the ratio is greater than or equal to 400. In the end, the ratio equals 16,000, which is greater than or equal to 400. So as a result, the assumption that z is small is valid. After rearranging the equation, the final answer for z is 1.4 times 10 to the minus 8. The fourth and final ionization process is where hydrogen diphosphate ion in liquid water partially ionizes to produce hydronium and HP2O7 4- or diphosphate ion. Ka4, or the fourth acid dissociating constant, is 5.6 times 10 to the minus 10. In constructing the Rice table, the initial concentration of hydrogen diphosphate ion is 1.4 times 10 to the minus 8 molar. Hydronium ion is 7.3 times 10 to the minus 2 molar, and diphosphate ion is 0 molar. The change is minus B for hydrogen diphosphate ion and plus B for both hydronium and diphosphate ion. The equilibrium concentration for hydrogen diphosphate ion is 1.4 times 10 to the minus 8 minus B. (7.3 times 10 to the minus 2 plus B for hydronium ion, and B for diphosphate ion. The equilibrium expression for Ka4 equals the concentrations of diphosphate ion times hydronium ion divided by the concentration of hydrogen diphosphate ion. If one plugs in the numbers, 5.6 times 10 to the minus 10 equals B times 7.3 times 10 to the minus 2 plus B in parentheses divided by 1.4 times 10 to the minus 8 minus B in parentheses. To determine if B is small enough to ignore, one needs to take the concentration of hydrogen diphosphate divided by the Ka4's value to see if the ratio is greater than or equal to 400. In the end, the ratio equals 25, and since it's not greater than or equal to 400, the assumption that x is small is invalid. One needs to either use the quadratic equation or successive approximation method to solve for B. For this part of the problem, like before, we will use the successive approximation method. In the first assumption, B0 equals 0. So after solving for B1, it equals 1.1 times 10 to the minus 16. In the second assumption, with B1 equaling 1.1 times 10 to the minus 16. In solving for B2, it equals to 1.1 times 10 to the minus 16. Therefore, since B1 and B2 equal, this is the final result. The final answers are as follows. Since x equals 7.3 times 10 to the minus 2, pyrophosphoric acid concentration is 0.18 molar. Trihydrogen diphosphate ions concentration equals X, or 7.3 times 10 to the minus 2 molar. Dihydrogen diphosphate ions concentration equals Y, or 4.0 times 10 to the minus 3 molar. Hydrogen diphosphate ions concentration equals Z, or 1.4 times 10 to the minus 8 molar. Diphosphate ions concentration equals B, or 1.1 times 10 to the minus 16 molar. And hydronium ions concentration equals 6.9 times 10 to the minus 2 molar. The pH of this solution equals the negative log of hydronium ions concentration, or the negative log of 6.9 times 10 to the minus 2 equals 1.16. The percent ionization of this acid equals the sum of X, Y, Z, and D divided by the concentration of pyrophosphoric acid, which is, after plugging its values, is 28%.